Okay, let the recording start then. Okay, so the question actually was this. Suppose I have a transistor. I'm drawing an NPN transistor just for definiteness. So what does it really look like? It's essentially looks like this, right? You have a N region, a P region, and an N region. Three regions sandwiched, right? N, there's a P in the middle, there's an N. Now, if you look at any one of the junctions, the junction essentially is something like this. You have an, say, if you look at the base emitter junction, for example, you have a P and an N, and in between you have a depletion region. As I said, this is what gives rise to the capacitance. There's three capacitance. It's a very tiny amount, but still a capacitance because this looks like an insulating region in between two conducting regions. Of course, why is the capacitance tiny? Primarily because the area, that's what the capacitance is proportional to, as you all know. The area for these devices will be very, very small. So the capacity to hold charge would be very small. So when you model this device, what you're really saying is that there is, so between these 2 points, there is this, whatever the PN junction was doing beforehand, that is whatever the base emitter junction was doing. And between the same 2 points, there's a capacitor. So whenever you have a situation like this, so there's this emitter, there's a base, whatever was happening between them, that is electrons were flowing between the emitter and the base, that's still happening. But in addition, you also have a capacitor between the same 2 points. Because the capacitor is between the same 2 points is basically in parallel. But that's a quick answer. The other way to look upon this is the model which works best. Basically, the idea is that these capacitors, they are very, very tiny. So at ordinary frequency ranges, they don't work at all. If they don't work, notice that if you put a capacitor in series, for example, with, say, the base connection, say this capacitor came here, then what would happen is that at low frequencies, they would effectively block all current from flowing into the actual transistor. That's not what happens, right? What happens essentially is that current can flow from the emitter to the base, but at very high frequencies, these capacitors also provide an alternative path for the current to flow, so that the injected current from the emitter to the base do not get to the base. Okay, that is remember the current which goes to the base directly, that's the one which gets pulled into the collector by the reverse bias. Just hold on, I need to open the door. Are you sure? Okay, I'm back. So, is that answer sort of understandable?
Sir, but the current flowing through both of them is the same, right?
Yeah.
Okay, but
Sorry, I couldn't hear the last part of your question.
so the current flowing through this capacitor and the emitter base junction, those they are same, right?
Hmm.
So, but that does
Again,
not
I
mean
can
that they are
only
in
hear
series.
half. No,
Okay.
if they were in, look, if these were like this, there is, first of all, when you remember, this is ultimately a model. It's not as if there's a real capacitor there. There's this junction which has some conductivity, some current can go flow from here to here anyway, but there's also a capacitance between the same 2 points. The best way to model that would be to assume that the actual transistor has, that is not the actual transistor, let's call this the ideal transistor, the transistor that we have been discussing using the Ebers-Moll model so far. We have not taken into account this possibility that at very high frequencies, the currents may get diverted out from the actual injection mode. Okay, that is what the capacitors do. They essentially divert the current away from the part which goes into the base and gets pulled into the capacitor, into the collector. Now, I also said in that video that this is really a simplified model of what's really going on. The actual model, which is more accurate at high frequencies, is quite a lot more complicated. We didn't want to go into that because this effective model, where you pretend that the transistor is as it was with just capacitors, which essentially, look, what we said was you have a capacitor here. So what is that doing? It's essentially diverting some current away from the base. And as a result, it's actually reducing the possible output current. Now, that is what phenomenologically happens in a transistor circuit at high frequencies. So, what we are really doing is we are trying to model the behavior of the transistor at high frequencies by using these three parallel capacitors. It's a model. It's not, of course, it's not what the transistor really is. It does not come with capacitances. But if you want to understand where these capacitances come from physically, it's because the junctions essentially behave like insulators, the depletion regions, and sandwich between two conductors. And this one, for example, the collector emitter capacitance, that's even more mysterious, basically because there is really no insulator between the collector and the emitter. But the way to understand that would be the base is very lightly doped, so it's almost an insulator. But these are just ways of understanding phenomenologically what's happening. A full-fledged high-frequency model of the transistor is really beyond this course, because that will require a lot more device physics than we can possibly squeeze in here. All I'm saying is what actually happens ultimately is that these pathways provide alternative paths for current to flow, so that the Ebers mode transistor, let's call it that, the ideal transistor that we talked about before, that is deprived of getting the currents. And as a result, it produces less of an amplification. Is that sort of
Yes, sir.
understandable?
Yes.
Remember, we are actually replacing the actual transistor by an effective model. And that this is the putting them in parallel is how they would work, because otherwise what will happen is phenomenological. If you put them in series, for example, they would have told you that at low frequencies the transistor gets completely detached from the circuit, because at low frequencies the capacitors would be open. And then of course is not what happens in a real transistor.
Yes, sir.
Okay. And one more thing, I didn't talk about that in the actual lecture, but there is one theorem which is of great importance here, really. So it's important at least that you heard about it once, even if we don't use it that much. So at very high frequencies, remember we talked about this, we have this source voltage and a load. There were, of course, other things like R1 parallel R2 and there was RS, but we argued that those could be ignored. At least remember, we are actually replacing the transistor by an approximate model anyway. So trying to be very precise about the other things isn't really worth it. You have to remember one thing: if you are using an approximate model, you should never actually try to calculate things too exactly with it, because that way it gives you a false sense that whatever result you're getting is perfectly accurate, which of course it's not, because your original model has approximations. And this is a very important lesson in all of physics. Physics, after all, deals with all approximate models. Sometimes the approximate models mimic the real world more closely, sometimes less closely. But you judge the success or failure of your model depending on given how approximate it is, how well does it manage to explain the world. So even if a crude model, a simple crude model manages to explain a world to say within 5% accuracy, I would perhaps consider that to be more successful than a very, very precise model with lots and lots of complicated parameters, which manages to give you 1% accuracy. Of course, there may be situations where you want the 1% accuracy. That's a different thing altogether. Okay, coming back to this issue, here we had three transistors, right? At least these were the three three capacitors, not three transistors. Stray capacitances which we are working in this case. The base emitter junction capacitance. Sorry, this is the base collector junction capacitance. This is the base emitter capacitance. This is the collector emitter capacitance. Now, we figured out what effect this would have essentially by replacing the transistor by its effective small signal model, and then we did a calculation. And in the end, what we saw was one of the three transistors, not all three, but only one of the three really contributed drastically. Okay. Before we go there, let me also point out one thing. Although I have only pointed out these three capacitances which come in with the physical transistor, there are other stray capacitances in the circuit. When you build a circuit, you have wires placed parallel to each other, right? So two wires placed close to each other, there will be a capacitance between them. It will be a very, very tiny capacitance, but at high enough frequencies, even such a tiny capacitance can provide enough pathway for currents to sort of get diverted through them. Once again, if you have two wires, let's say like this, and you're talking about the capacitance between them, the capacitance really comes in here. That is, it can divert the current which would otherwise flow through the capacitor uh, through this wire, divert the current from one wire to another. That exactly is why stray capacitors come in parallel. And you would have had a stray capacitance here between these wires, another stray capacitance, which are all effective stray capacitors. That is, you don't really have a capacitor there, but all the circuit components put together, they behave like there's a capacitance. So when I say this is CBE, I really mean CBE is really what the transistor has, also what the wiring has. Okay. Similarly, CE that you saw in the circuit is really contributed both by the capacitance and this wiring, because that's the capacitance which you connect between the collector and the emitter. Of course, capacitors which are in parallel, they add, right? So basically, the actual capacitance that which you really see, when I say actual, I mean the effective capacitance you see between the collector and the emitter is a sum total of the capacitance provided by the transistor itself, also by the wiring on the output side. Now, I don't know whether anybody remembers this, but of the three capacitors, in the final formula for the cutoff frequency, only one of them actually contributed by a large amount, which was this one. The base to collector capacitance. The other two ultimately dropped out of the expression, or at least when you made this approximation, you could see that you didn't have to bother about CB's other two. But what is so special about this one capacitor compared to the other two? Can anybody tell me that? Size-wise, all three capacitors are more or less the same. CCE is a bit smaller, simply because there is no real collector emitter junction. But CBC and CBE, for example, are more or less the same in size. So why would CBC contribute more? Physically, can you give me an idea as to why that would happen? Or at least tell me this: why is CBC placed differently from the other two capacitors? What's so special about that? Any guesses? I'm asking you to guess. What's physically different between this capacitance, which joins the base to the collector, and what is the difference between that one and the other two? Any ideas?
Sir, base collector is reverse bias, so it will have a wider depletion region, I think.
Okay, but well, you're right. Base collector is reverse bias, so it will have a wider depletion region. But a wider depletion region, if anything, would have made that capacitance smaller than the other two, right? A smaller capacitance, remember, means a higher impedance. If it's a higher impedance, it would and because these are in parallel, so remember all three are actually working by diverting current away from the active part. So a higher impedance would really mean that it's going to divert less, right? You are right in saying the CBC is going to be slightly smaller. So I was not really correct when I said all three are exactly equal in size, but I didn't say they're exactly equal. I just said they're of the same order. CBC would typically be smaller, but despite being smaller, it actually is the one which is going to contribute more often than not. Unless something very unusual happens, CBC contributes. So my question to you really is this: can you spot some some aspect in which CBC, the base collector capacitor, is differently placed than the other two? Just think of the input and output. Which one is the input here, by the way, for this transistor, for this circuit? Which two terminals give you the input? For the base, for the common emitter amplifier, this is a CE amplifier, right? For the CE amplifier, the input is what? Or between 2 points, you give the input. Which 2 points? When I say input voltage, where do I give it? You can see that, of course, on the circuit. It's between the base and the emitter, right? And the output is given between the collector and the emitter, right? That's why you call it the common emitter. Emitter is common between both ends. So if you look in terms of the input and the output of the amplifier, and you now tell me what is special about CBC, which the other two don't share. Okay, let me just give you a hint. If you thought of the amplifier simply like this, just as an abstract entity, something which takes in a voltage, puts out a voltage. So in our case, the input side, this is of course a base, the output side is a collector, and the emitter is a common, the ground. Okay. If you thought of it, this whole thing abstractly along these lines, the CBE would be sitting here, right? Between the input and the ground. The emitter, remember, is the ground. CCE would be sitting here. But what would this capacitor be doing? It would be sitting like this. So what's different between this one capacitor, the base collector capacitor, and the other two? Any ideas? You can see that, right? You can see that there is a big difference. What is the big difference?
So this capacitor has a feedback-like connection.
Has a? Sorry.
Feedback-like connection.
Well, not really, but I guess you are saying, you are looking at the right thing. All I meant here was not really feedback, but really is connected between the input and the output, right? It straddles the amplifier. The other two are either on the input side or the output side. Okay. So actually there is a result which is a very important result. In fact, I'm not going to talk any more about this now, for the simple reason that this is one of the problems in your next problem sheet. It's called the Miller effect, or some people call it Miller's theorem, which essentially tell you that if you have an amplifier with an impedance which straddles both sides, which is connected between the input and the output, you can think of that as a feedback, but it's really not meant to so much feedback the output to the input. Is basically meant to connect the input to the output via an alternative pathway, bypassing the amplifier. If that happens, then because of the Miller effect, this impedance ends up looking very, very different. If you look at the effective value of the impedance, this will end up looking very different from the output side. This is something we are going to have a problem on in the problem sheet, and there I will hope to give enough details in the calculation so that you can explore for yourself what Miller effect really is. So just to sort of state this at this stage. The reason why CBC ultimately dominates the upper cutoff frequency is basically a result of what is called Miller effect. Of course, you don't need to know that. You can directly do the calculation yourself. But still, the Miller effect is a nice, handy thing to know about because it comes in several times in amplifier theory. In other cases for more complicated amplifiers as well. So we will talk about that in the problem sheet. Okay, any other questions? This whole issue of calculating one cutoff frequency for each capacitor and then deciding which one is the upper cutoff frequency, is that clear? That is, this was for the low frequency part. We had 3 capacitors in the circuit and then we said take one capacitor at a time, calculate the cutoff frequency and then find out the answer. Was that procedure clear? I'm assuming it's clear because nobody is saying it's not. Okay, does anybody have any questions? I'm going to give you 5 seconds to unmute and ask because then I'm going to move on to the next topic. Okay, and by the way, this is a nice time, enough time to make an announcement. Class test 3 will be next Wednesday. And in fact, we will have a class test every week till the end of the semester. Because I guess that's the only way I can ensure that people are really keeping up and not falling way behind. But that's not the only reason. The other reason is we will not have a proctored exam this time. So we will have a reduced weightage for the NSEM, which means that I have to take more class tests in order to make it a decent evaluation. Okay, so that stunned silence essentially means that people are so shocked that they can't respond, or what? Or they have all gone to sleep. Okay, they have all gone to sleep. Okay, so since there are no other further questions, I'm going to move on to a previous topic, not really a next topic. We were talking about negative feedback in the previous discussion class. Negative feedback actually is going to be very, very important for op-amps. We have started talking about op-amps in the last video, and one more video will be uploaded right after this class actually. So take a look at those. But we were talking about this specific negative feedback scenario for a voltage to voltage amplifier. And we use a sort of abstract amplifier symbol to talk about that. We will also talk about that in abstract language today, but we will sort of be a bit more specific. So if you have a voltage to voltage amplifier, we want to give feedback. Then what happens? You have to take out a voltage, right, from the output, and you have to feed in a voltage to the input. So how would you take out a voltage from the output? How would you connect your feedback network to the output side? So there's this feedback network. Somehow you have a network which draws no current from the amplifier. Let's assume that. So that's of course an approximation for most situations. But this amplifier, what it does is takes the output voltage. This part, sorry, not the amplifier, the feedback network takes the output voltage, takes a fraction of that, calculates a fraction of that, or somehow produces a fraction of that, and puts that back to the input. So how would you sample the output voltage? Would you connect it in series to the output or in parallel with the output? How would you connect? connect that. That is, there are two choices. When you connect this output, do you connect it like this? That's one choice. The other possibility is you open up this wire and connect it like this. Okay, let me just do it on the input side, at least. Let's say on the input side, we could do something like this. My lines are looking horrible, but that's fine. So is this what you would do? This is called the shunt out, series in combination, or shunt series feedback. That is, on the output side you have shunt, on the input side you have a series. Shunt is just another fancy way of saying parallel. So is this how you would connect it? Or would you connect it in series on both sides, or shunts on both sides? Or maybe shunt in series out? So any ideas how you would connect the circuit really? If you have an amplifier, you have a feedback network which you want to connect to the amplifier, how would you actually connect it? There are four possibilities, right? Because you can connect it either in parallel or in series. So you have shunts or series for both the input and the output. So you have four distinct possibilities. Which one would you use? And this is something which you can answer just based on logic. You don't need to know this beforehand.
So, shouldn't that depend on what we need?
Yeah, of course, it depends on what you need. But remember, we are talking about voltage to voltage amplifier specifically. So our voltage has amplifier has a voltage input and a voltage output. So what we want to do, what our network to do, is sample the output at the output voltage and feed a fraction of that back to the input. That is what we want in this case. And you are very correct. If we wanted some other kind of amplifier, for example, if it had been a voltage in current out amplifier, then you would have to sample the current on the output side and feedback the voltage on the input side. But in this case, I'm talking specifically about a voltage to voltage amplifier. So how would you connect it? So there were four possibilities, as I said. In fact, each of one of the four possibilities is the correct one for one of the four kinds of amplifiers. Remember, you just think of currents and voltages as the inputs and output possibilities. You can have four kinds, right? V to V, current to current, current to voltage, voltage to current. That is, depending on your application, you are feeding in an input voltage signal, you want an output voltage signal. Here, your input signal is better thought of as the current which comes in from somewhere, and what you want out of it is a current, a larger current maybe. You don't care so much about the voltage, you care about how much current you're getting. Similarly, current to voltage, voltage to current. These are the four possibilities. And this shunt series thing, there are also four possibilities, and they actually go hand in hand with one of the four kinds. The question I have for you is this. If you have a voltage in voltage out amplifier, the standard amplifier which amplifies the voltage to give you another voltage, what kind of feedback would you use there? And as I actually said, this is just logic. And I have really told you the answer. What you want for a voltage to voltage amplifier, this is the one we are looking at, you need to sample the output voltage, right? So your network should be able to figure out how much the output voltage is, or at least should be able to get the output voltage as a result. How would you get the output voltage? Which connection gives you the voltage? The parallel one or the series one? If you have two possibilities, one is the one connection I've shown, and the other is like this. At the voltage, this is the output voltage. The other could be you could connect the network in series so that it takes signal from here. Each of one of the two would actually be able to sample the output voltage. This one or this one?
Parallel.
Of course, right? This is simple. After all, the network can only, the feedback network can only feel what it is getting. And in order that it gets the output voltage, it has to be connected across the output terminal, right? So it has to be this one. So it has to be shunt out. It has to take shunt from this side. And the output, remember what we want. We want the actual input to the amplifier itself to be the input that you are giving minus beta times VO, right? The minus sign is fine, but you want to add two voltages together. The minus sign is taken care of by either a negative sign for the amplifier itself, amplification itself, or a negative sign somewhere here. But ultimately, what you want to do is add two voltages to get a full voltage. How, under what situation do voltages add? When you have voltages in series or in parallel? Yes?
That should also be parallel.
No, if you have two voltages in parallel, they never add. Voltages in series add, right? You want the voltage between these 2 points, the actual amplifier input, to be a sum of this voltage and this voltage. And that can happen only in series. Remember, currents add in parallel, voltages add when they're in series. So if you want to add beta VO with a minus sign, but add minus beta VO, let's say, to VI, you have to actually put the feedback in series with the input. These are the details we ignored in the last class when we just talked about some kind of summation happening. When you really want the summation to occur in a circuit, you have to ensure that the circuit that we drew the last day essentially said that you have an amplifier, you sample the output somehow, I didn't say how, then take a fraction of that and somehow add that to the actual input with a minus sign and you get negative feedback. Okay. The question is, how do you actually add? To add two voltages, you have to put them in series. To sample the output voltage, you have to put it in parallel. If this had been a current to current amplifier, the situation would have been exactly reversed, because you would have to sample the output current, and to sample the output current, this connection will simply not do. The output current, remember, is the current flowing here, right? So if you put this in series, it's going to sample the output current, not if you put it in parallel. If you put it in parallel, it's actually going to divert a part of the output current away. That's not what you want. Okay. Similarly, you would want to add the current with a minus sign to the input. If you want to add two currents, the way to do that would be put it in parallel. So whether it's shunt out, series in, shunt in, series out, whatever, all the four possibilities, that actually depends on what kind of an amplifier you're looking for. And I will not go into the details right now. I will ask you to think about it. All the things we said about input impedance and output impedance, you want huge input impedance, small output impedance, that's actually true for a voltage to voltage amplifier. For a current to current amplifier, you actually want exactly the opposite. Think about it. And negative feedback, once again, does what you really need. It actually, whereas negative feedback here, for this circuit, the one which we are discussing, the negative feedback actually raises the input impedance. For a current to current amplifier, it actually lowers the input impedance. So it actually does what you really want there. Why you want that in a current to current amplifier, and how does negative feedback help in that? I will urge you to think about it yourselves. And I will also give you problems to think about help you think about that. But the upshot is negative feedback helps in almost everything. Except in the gain, it reduces the gain. Okay. And the final topic I will talk about today, there will be enough of negative feedback in the op-amp lecture that I'm going to upload today, because if anybody has seen the previous op-amp lecture, you would know that the op-amps are wonderful circuits, but they don't really work like an amplifier, simply because they have way too big gains and that makes them saturate. So today we are going to tell you, in today's video that's going to be uploaded soon after this class, I will tell you how to get linear circuits using op-amps. And those linear circuits will actually have to hinge completely on negative feedback. Now, I will wrap up today's class with the opposites. So are there any questions about this before I move on to the last topic of the day? So the last topic of the day essentially is just the opposite of what I've been talking about right now. We were talking about negative feedback, but what if you have a positive feedback on an amplifier? Of course, positive feedback could increase the gain, but sometimes it might end up increasing the gain so much that the circuit becomes useless, or the circuit begins to do something entirely different. Put very crudely, if we remember, we just saw that this was the formula. Last day we saw this, right? This was the formula for the overall gain of an amplifier with negative feedback. So what happens if you have positive feedback? Well, with under negative feedback, this beta A naught was positive. So 1 plus beta A naught was more than 1. So the gain was coming down. With positive feedback, of course, all that's going to happen is that you could either keep on using the same formula with beta A naught negative, or you could just change your sign convention and you would end up with this formula. So can anybody spot what can go wrong with this? If you have a formula like this, why can this lead to trouble? Of course, here beta A naught is positive, so is the case here. I've just changed the overall sign to indicate that now you have positive feedback. So this is for negative feedback.
Beta naught may become 1.
And then what will happen?
Equal to 1. Then it will blow up.
Okay. So blowing up, of course, never really happens, right? So if your theory is predicting a blow up, it usually is time to look for a better theory. Look for that something in your theory actually went wrong. Now, there's a whole bunch of circuit theory here called stability analysis and something called Nyquist criterion, and all that is taught at an advanced level. We will not go into that simply because we don't have the time to go into that. It's a fascinating topic, but for our purpose, it's very easy to think about one thing. If beta A naught becomes 1, what is really happening is something like this. You have an amplifier. Okay, no, not the dash in front. You just have an amplifier. This is a triangle. You're taking its output, a fraction of that, and feeding it back to the input. And remember, now you're feeding, so you were giving in VI, you were getting VO, and you're now feeding in beta VO in and adding it to VI. You're not subtracting, you're not reducing the input. Now, just think about it like this. Suppose I managed to get beta A equal to 1. Then what would happen is, even without the input voltage, whatever output you have, well, a fraction of that will come back. You get beta VO. And then A times that will go back. So you get A beta times VO. But A beta is being 1 means whatever output you give, that comes back to you as it is. So basically the output self-sustains itself. Okay. So this is the condition basically for the output becomes self-sustaining, which is just a fancy way of saying that the output can actually survive even without an input. In other words, the circuit actually starts to oscillate. Okay. Now, that's a bad thing for an amplifier. You don't want your amplifier to start oscillating. However, it is a good thing if you are building an oscillator. So this is actually called the Berkhausen criterion, or this particular thing, beta A naught equals 1, is a special case of something called the Nyquist criterion. Big names named after people who unfortunately had big names. But basically, all you're saying is if beta times A naught is equal to 1, your output can come back and bootstrap itself. So basically, it comes back just so that the output can manage to be amplified back again to its original value. So it sort of keeps on going forever. Now this of course looks like magic for two reasons. One is, where is the power coming from? If there's no input, how do you get an output? But that is really not a question. After all, even in an amplifier, you get a bigger output than an input. So you would also ask, where is the power coming from there? And the answer is, it's coming from the power supply. The amplifier, of course, doesn't work without the power supply. The actual power comes from the power supply. Okay. All the amplifier does is convert the steady voltage which the power supply would have given you into an oscillatory voltage. Okay, so it's not, even an amplifier produces more power than goes in, but this extra power comes from the power supply. An oscillator oscillates without any input power, but there is an input power. The power supply, the batteries give input power. So that's not a mystery. But the other question would be something like this. I just said, okay, let's put Vi equal to 0, then whatever VO there is will come back and sustain itself. So your question would be, where should this VO come from? If there's no Vi to begin with, why should you have a VO? Any idea about that? How can you have an output even without an input? To begin with, of course, if you have an output without an input, you have just figured out that it's going to self-sustain. Then it's going to stay there. How do you get an output without an input in the first place? Any guesses? And this is how an oscillator works, by the way. Somehow it manages to get some output without an input and latches onto that. But how does that happen? So if there's no input, does that mean that the circuit has no signals whatsoever?
Maybe there's a power source inside the
Well, of course you
amplifier,
need the power
or maybe a
source in
biasing.
order to sustain itself, but a steady power source would also not be a signal. But no power source in the world is really steady. And there are thermal noises. Simply because of temperature, there are standard effects you study in statistical mechanics. In the last semester, you talked about that, right? Thermal fluctuations. These thermal fluctuations are actually going to give rise to tiny signals, very, very tiny signals. But if you have an amplifier for which beta A is more than 1, then what's going to happen is the tiny signal is going to go to the output. Let's say beta times A is 2. Then you have a tiny signal which goes out and comes back in as twice itself. Then it goes back and comes back in at twice that, and so on. So even a tiny signal grows very rapidly. Of course, if it kept on growing, then we would have trouble, and it can't keep on growing. After all, you have a power supply, so that it's limited by the size of the power supply. It can't really go beyond the power supply size. So what really happens in an actual oscillator circuit is something like this. You start with an oscillator which has a huge gain for low inputs, but you have to somehow ensure that the gain falls, becomes smaller as the output rises and reaches a value of 1 by beta at a particular frequency, at a particular output level, and then the output stays steady. We will discuss how that happens soon, but before that, there's one more important aspect about this criterion that we have to specify. In most situations, A0 will have A0 is the input, of course, the output to input ratio. But the output to input, these are, if you think of sinusoidal signals, then we would usually be using complex signals. We have already done that when we discussed AC circuits. And A0 would be a complex number in general. And so would beta. Beta could also be a complex number. It could be frequency dependent. And there could be a phase shift. So basically, when you say beta A0 equal to 1, the actual criterion talks about more than just a single numerical value. Why? Because a complex number being equal to 1 means two things. It means its magnitude is 1. It also means its phase is 0. So two things has to happen. The output has to come back exactly to the input in such a way that it manages to self-sustain as far as magnitude is concerned. It also has to come back exactly in phase. Then and only then do you have oscillations. Now, let me just give you an example of an oscillator that's going to be quite interesting. One very useful oscillator, actually. And for this, I have to borrow a result from my lecture today, which is going to be uploaded soon. I talked about op-amp circuits, so here I'm just taking a result from there. So those of you who have not seen any of the op-amp lectures might feel a bit lost, but all you really need to know is this, that this circuit that we have drawn here is an amplifier, this one. And if these resistances are R1, R2, the only thing that you really need to know is that this has a gain. The overall amplifier has a gain of 1 plus R1 by R2. Okay, that's all you really need to know. So is this clear? So I'm just talking about an amplifier which I've somehow made, whose gain is 1 plus R1 by R2. It's a positive number, so it's called a non-inverting amplifier. But the input to this, this is of course the gain which I would have if I gave some signal here, the output will be 1 plus R1 by R2 times that. I don't really give a signal here. What I do is something else. I take the output and take this circuit and connect it here. So can you see what I have done? I have taken this RC series, RC parallel combination, connected the output back to the input via this circuit. And I'm not sure how good your memories are, collective memories that is, but this circuit, does it ring a bell? If I draw it like this, does this circuit ring a bell with anybody? So where I give an input here, some sinusoidal input, and I get an output here. Okay, by the way, notice that the two situations have been reversed. Here we are saying output comes here, output to the amplifier comes here, but output to the amplifier is really input to this circuit that I have. And the output of this circuit, which is this voltage, that's going into my amplifier as input. Okay, so when I say output and input, it may get confusing because it depends on which one we are referring to. But can anybody tell me, remember anything about this circuit, RC? Okay, quickly, at low frequencies, which one has a higher impedance, the capacitor or the resistance? Resistance, of course, has the same impedance at all values, but which one has a higher impedance at low frequency? When frequency becomes lower, which one will dominate in impedance?
The resistance.
Resistance has the impedance of R at all frequencies.
Sorry, sorry.
The capacitance has an impedance apart from the J, which it talks about the phase. Capacitance has an impedance of 1 by omega c. So at low frequencies, of course, R will dominate. R will have a larger impedance. You're right. Is that true? Is it at all true? People seem to have completely fallen asleep. Of these two quantities, at low frequencies, which one would you expect to be larger? When you go to sufficiently low frequencies, the capacitor will have the larger impedance. So this is a series combination, right? So what will this essentially look like at low frequencies? There are two things in series and one impedance is much bigger than the other. What does the series look like? You had two resistances, for example. One was 1 kilo ohm and another 100 kilo ohm. Which one will the series combination look like, the 1K or the 100K? Yeah, in series it looks like the bigger impedance. And in parallel, it looks like the smaller impedance, right? Why? Because parallel gives you different branches, different paths for current to flow. And the smaller impedance, of course, takes most of the current. So this one, actually, at low frequencies, this looks like this, C, and this end looks like R. So this looks like a CR network where R is the output. So here, the output leads the input. I hope everybody remembers that much. If you have a CR parallel series combination, the output will be leading. In an RC combination, the output will lag. But here, for low frequencies, this looks like CR. Just think about it. At high frequencies, the C will be very small impedance. This will look like an R. This will look like an C. So circuit will look like RC. The output will lag. What is important is somewhere in between, the output will exactly match the input in phase. What that means is this beta, this condition that we wrote down, beta A equal to 1. Remember, this also has a phase part to this demand. The phase would be exactly 0. That is, the output and the input will be exactly in phase at only one frequency. And so this circuit will oscillate only at that frequency. In the next discussion, we'll talk a bit more about this. But let me wrap up today with one thing. This circuit was essentially designed by one MIT graduate who was working very hard trying to figure out ways of controlling the gain of this amplifier. We are going to discuss a bit about that in the next discussion class as well. The circuit has a name. It's called the Wien Bridge oscillator. It's one of the most common oscillators that people use and make. But the important thing is the fellow who did his PhD essentially on designing this circuit, what he did was, after doing his PhD, he rented a garage, teamed up with a friend, and started making these oscillators. And that's how one of the biggest companies in the world was born. This fellow's name was Hewlett, and his friend, of course, was called what? Packard. Yeah. This is the beginning of the HP collaboration. That is, today's huge giant HP was born out of a garage basement and essentially building this circuit, which was a PhD work of one of the beginners. Essentially, his entire PhD was measuring resistance of light bulbs. How light bulbs come in the picture, we will talk about that in the next class. But it's interesting that people actually get to become multi-billionaires doing these things. Also, apart from the academic interest in learning about these things. Okay, I have to go today. Just reminder, Wednesday examination, but the topic will be transistor amplifiers. All of it. Biasing, AC behavior. Op-amps will cover in the exam next week. The week after this. So next Wednesday's examination only about transistors. Can I have to run today because I have a meeting, which I'm actually skipping right now to be here.